Alright, this is the second part of the single-phase fluid flow modeling video, and I already talked about these discrete differential operators. Now it's time to talk about the rest of the code. In the system that we're dealing with, we only have one unknown, which is pressure of water. Alright, if we had a two-phase system or a three-phase system, we would also have saturations as the unknowns of the system. Alright, but because we're dealing with in a single-phase flow system here, the pressure of water is the unknown of the system, is the only unknown of the system. And because we only have one unknown, we need one equation in order to solve the problem. If we had two unknowns, we would be required to have two equations in order to solve the problem and find the solutions. Alright? So in this case, we have one unknown, so we have one equation. What is that equation? It's the pressure equation of water, which some researchers call the flow equation. But I prefer to use the name the pressure equation, which is written here. The pressure equation is actually the conservation equation of the fluid we're referring to, which in this case is water. The first term of the conservation equation is the accumulation term, and as you see, we have time here, and this is the numerator of the accumulation term. Alright, this is the numerator. And this is the flux term of this pressure equation. You see the flux here, or the flow rate here, and this is density. Alright, well, I'll get to this in a minute. And as you see, this is the pressure equation, and in the following I have added the boundary conditions. Alright, I sometimes call them internal boundary conditions because in this case they're wells. Alright, great. In order to solve this pressure equation, which is a non-linear equation, I'm going to use the Newton-raphson method, which is a great method in order to solve a set of nonlinear equations. Of course, here I don't have a set of nonlinear equations, I only have one nonlinear equation. But there's no problem. But there is a problem here. In the Newton-raphson method, I am required to differentiate the pressure equation, or whatever equation I'm dealing with. So how can I do that? How do I want to differentiate that equation? So this is where MRST shows itself. I'm going to use a very great capability of MRST to make this happen. I'm going to use automatic differentiation in order to differentiate the pressure equation. In the automatic differentiation, actually MRST uses the forward mode of automatic differentiation, and of course I'm not going to get into the details. I'll probably make another video on this topic. And in order to use automatic differentiation, I have used the function init variables ADI, and the input argument of this function is the initial pressure of actually the system. Alright, this is the initial pressure that I talked about in the previous video, and this is the input argument of this function. And if I run this code, of course, I turned off actually the computer, so I need to actually add the folders of MRST to actually the MATLAB path. Great. Start up. In the previous video, before I started recording the video, I had done this, alright? And you should do the same. But if you have already added the paths or added the folders to the path of MATLAB, you don't need to do it again, alright? Great. Alright, so I added the folders. Now I can use this function because it is added to the MATLAB path. So let me run the code until this line. Of course, I'm not going to keep you waiting. So alright, great. And as you see, this is the initial pressure of the system. Let me close this figure. The initial pressure of the porous media. If it shows it to me, alright, this is the initial pressure. And as you see, because it's a one-dimensional model, all the pressures are the same. And let me run the next line in order to see what is inside this variable. And as you see, this variable is a struct, and it consists of two fields. The first field is val, which is exactly the values here, all right. And the second field of this actually struct is the Jacobian, all right, which is a sparse matrix. If I use the function full, I'll be able to see the full form of this sparse matrix. All right, let me store it in the variable a. I don't have it. I not used this variable previously, so it's not going to make any problem. It's going to create any problem. So let me store it in the variable a and use the function full to see the full form of this sparse matrix. P underline AD dot Jacobian, and first element of this great. So as you see, this is the full form of this sparse matrix. Alright, this is a sparse matrix, this is the full form of that. Great. So we need the Jacobian to solve the problem, which I'll talk about it in a minute. Here I have specified the number of time steps, which is 52. The total simulation time is a year, and here I have calculated the size of each time step, and this is the tolerance, and the maximum number of times the Newton-raphson loop needs to be iterated, and if the number of iterations exceeds this number, we say that the solution, or the actually it did not converge. All right, and it's terrible news. All right, here I have created a struct in order to store the solutions to the problem. And as you see, the first solution actually is the initial conditions of the system. Here I have started actually I have used the while loop in order to actually solve the problem, and each pass is equivalent to one step, one time step. All right. So each pass gives me the solution to one time step. So let's talk about the first pass. If you learn how the first pass is done, you'll be able to understand the other passes as well. As you see, here we have initialized the variable t, which gives me the time of the simulation. Of course, it doesn't give me the runtime, it gives me the simulation time, which is different. And at first the time is 0, and as the time goes on, this number will be added depending on the time step size. All right. And I have also initialized the variable step. At first, step is 0, but for the first time step, it becomes 1. The second time step, it becomes 2, etc. And here I have used the function ifprintf in order to print actually a report of the simulation in the command window. All right, here I'm going to use the Newton-raphson method in order to solve the problem. At first, I need to specify a residual number, and afterwards it will be updated. All right, which must be a very, very small number. All right. At first, because I have used a while loop, I need to initialize it, and I need to enter this while loop. So I have considered a big number for this variable. I would be able to choose any number greater than the tolerance that I have specified. All right, but to make it very clear, I have used a very big number. All right, great. And here I have chosen, and actually I have specified the initial pressure, which is actually calculated in the previous time step. But in this case, because I'm in the first pass of the while loop, P underline AD is the initial pressure that I have here, the initial pressure. All right. But if I'm in the second loop, if I'm in the second pass of the loop, all right, this is actually the solution to the previous time step, which is calculated here. All right, great. So this is in the first pass, this is the initial conditions, but for the second pass of the main loop is this. For the second pass of the main loop, this is the condition, the solution to the previous time step. All right. For the second pass, this is the solution to the first time step. For the third pass, this is the solution to the second time step. All right. Great. And I have initialized the variable iter counter in order to count the number of times this loop iterates. And this is actually the Newton-raphson method, because in the Newton-raphson method, in order you need to solve the problem multiple times in order to solve the problem. All right, in order to find a solution to the problem and make the residual and less than the tolerance that you have specified. And what is residual? Residual is this variable, which must be a very, very small number in order to solve the problem. All right, it must be actually less than the tolerance, and tolerance is a very small number. And this is one of the conditions of this while loop. All right, if the residual number, if the residual norm is less than the tolerance, we have actually gotten to solution, and we have solved the problem. All right, so we don't need to continue this for loop, and actually we have solved the problem, and the results will be stored here. All right, great. At the beginning of this while loop, I have updated the density of the fluid for the initial pressure and this pressure, which you see here, and I have also updated the pore volume, which is the initial pressure, and this pressure. For the first pass, this is for the first pass of this while loop, this is actually this pressure. As you see, for the first pass, these two pressures are the same. But for the next pass, it is actually, for example, it is guessed, This number is guessed, because in the Newton-raphson method, we need to guess, the solution, all right, in order to solve the problem. So for the next passes, these pressures are guessed, and even for the first pass, this pressure is guessed. But we need to guess a number. So what number do we choose? We choose the initial pressure as a guess. All right, that's what we do. Here I have calculated the gradient for height of the model, the gradient of the centroids of the cells using the operator gradient or grad. Then I have used this variable here, actually in this Darcy equation. What you see here is the Darcy equation, and this is the flow rate, which you see here. This is the transmissibility that we calculated previously, and this is the viscosity. And what you see here is the pressure gradient as the pressure due to actually difference in depth. All right, this is exactly the Darcy equation, and we use this flow rate in this pressure equation, which is the only equation that we have. And as I told you, this is the accumulation term of this conservation equation, and this is the flux term. And as you heard, I use different names for this equation. It's the pressure equation, it's the conservation equation of water, or I could say that it's the residual equation. All right, and actually this is the residual value that we have. Here I have added the boundary conditions. In this line I have calculated the production rate, and then in this line I have specified the boundary condition for the production well. Pressure equation in the production cell, whose index is 50, minus production rate. All right, and for the injection well, I have specified the boundary condition in this way. I have the injection flow rate, and this is exactly the way I define the boundary condition for the pressure equation. Of course, I could use another method in order to determine the boundary condition for the production well, because I have the bottom hole pressure for the production well, I could use this method in order to specify the boundary condition. And what I need to do is to write this: the pressure of the cell in which the production well is perforated minus the bottom hole pressure. Alright? This is another way of specifying the boundary condition for the production well. Alright, here I get the Jacobian of the pressure equation, and here the residual of the pressure equation, and in this line I have received the increment that we need to get in order to update the guessed pressure that we have. This is exactly the way how the Newton-raphson method works. This is increment, and we add actually the previous pressure to the increment in order to solve this guess pressure and find a new guess in order to solve the problem. Alright, and that's it. Here I received the residual norm, and here I have updated the number of iterations. Great. And in this line we print a report of what had been happening, and if actually the solution, we have gotten to the solution and we have solved the problem, we no longer need to continue this for loop, this while loop actually, and so we will be required to store the solution, alright, for this first time step. And after that, after storing the results for the first time step, we'll get to the next time step, which is the second time step, to solve the problem for that time step. Alright? Great. Alright, so we're done. This is all the things that I needed to talk about, and now it's time to run the script. Let me actually comment this line. Of course I didn't have to, but let's show you the results. As I told you, this is a one-dimensional model. As you see here, this is one-dimensional, and these are the reports that I told you, and this is the output that you see here. The water is being injected through the injection well in the first block, in the first grid block of the model, and it is also being produced through the production well in the last cell of the model. Great. Alright, now let's run a multi-dimensional model. Let me scroll up here. I'm going to have a two-dimensional model, so let me discretize the model in the y direction. I'm going to have 10 cells in the y direction, reduce the number of cells in the x direction to 10 in order to reduce the runtime, and reduce the length of the model to 50 feet. 50 feet in the y direction. Alright, let me also reduce the simulation time in order to observe the variation in pressure more easily. 10 days. and let's run it. All right. As you see, there is instant pressure reduction in the reservoir, and it has some reasons. The first reason is that the injection rate is low for this reservoir. Another reason is that the compressibility of water is very low. So when water is produced in the production well, it creates instant pressure reduction in the reservoir. So, what I can do is to, let me stop it. Let me stop the program, as you see. All right. Uh, let's increase the flow rate to 2,000 stuck tank barrels per day. I think it's going to be enough in order to maintain the pressure in the injection. As you see, there is some pressure maintenance in the injection well, but it looks like it's not enough. So let's increase the injection rate more, 8,000 stuck tank barrels per day. And the model is very small. The model that we have is very small, 50,000 feet in the X direction, 50,000 feet in the Y direction. And so when water is produced in the production well, it creates instant pressure reduction in the reservoir. So we have to, that's why we have to inject 8,000 stuck tank barrels per day in order to maintain the pressure in the injection well, as you see here. All right, that's it. That's the case that I was gonna run for a single porosity porous medium. And now let's get to the fractured porous medium. I have used an already defined fractured actually domain in MRST, which you can find in the geothermal module of MRST. I'm going to use that domain and the model which is used to simulate fractures is the single continuum or the equivalent continuum model. The equivalent continuum model. In this model, for the fractures, we consider grid blocks with porosity equal to 1 and permeability equal to a very, very high value. All right, in order to consider the presence of fractures, and this is what is done in the equivalent continuum model. All right, so let's run this code. The only difference between this script and the previous script is actually the first part, which is the definition of the domain. And as you see here, I have loaded the data or the information of the fracture domain, which is in the geothermal module, and it's actually a three-dimensional model. So what I have done here is to remove the cells of all the layers except one, because I'm not gonna make it last so long, because it's got a lot of cells, a lot of grid blocks, and so it's going to have a very long runtime. So I have only one layer of this model here, and I have removed the cells of the other layers using the function remove cells. And here we can see what the grid looks like. And this is the grid that we have. As you see, this is two-dimensional, and the things that you observe here are the fractures. These are fractures. These grid blocks represent the fractures that we have. And as I told you, these fractures have a porosity equal to 1 and have a very, very high permeability. All right. Compared to the matrix grid blocks. Alright, now let's run the rest of the code, and as you see, there's no difference between these blocks of code with the ones in this script. So let's continue running the code and see what the output looks like. Alright, where is the result? Here it is. This is a two-dimensional view of the model, and water is being produced through the production well, also injected through the injection well in this grid block. And as you see, this injection well is trying to maintain the pressure in the reservoir or in the porous medium here. Alright, that's the whole thing I was going to talk about, and I hope you learned something. Thank you everybody for being with me, and hope you're having a great day.